Okay, so this is part 2 of the section 5.1 notes. So we have been talking about exponential functions, and we looked at the graph of an exponential function. Remember, the exponential function will always look like this and will always have these same characteristics. And so now we're going to talk about a special function, a special exponential function that occurs frequently in economics, biology, physics, business, etc. is y is equal to e to the x, where the natural base e represents an irrational number. So this e is just a number, kind of like pi. Pi is always 3.14159, so on and so forth. Same thing with e. E is always 2.71828, so on and so forth forever. Just like with pi, you've got a pi button on your calculator. Same thing with e. You've got an e button on your calculator with this number built in. So you don't have to memorize it. It's built in. And so e is just a number. And because it's just a number, we can use it as the base of our exponential function. Because remember, our exponential function is just some number raised to the x power. So we've got e, which is some number, 2.718, so on and so forth, raised to the x power. And so when we graph y equal e to the x, it looks exactly like all the other exponential functions. Notice it's got a y-intercept at 0, 1. It continues up and to the right. It comes down on the left towards the axis without ever touching or crossing the x-axis. So on the top of the next page, we have an example here. And so I'd like you guys to pause the video and try this one on your own. Okay, so on this one we have f of x is equal to e raised to the x over 4. If we're asked what is the base, well, the base is e. And the exponent is the x over 4. If I'm looking to find -1, I'm just going to plug -1 in for x. So that's going to be e to the -1 over 4. And we can put that in our calculator. You should have an e button on your calculator. And so when you put it in the calculator, you end up with 0.78 approximately. If we're looking for f of 0, we're plugging in 0 for x, so we get e to the 0 over 4. Well, 0 over 4 is just 0, and anything to the 0 power is always 1. If we're looking for f of 1, we put 1 in place of x, so we get e to the 1 over 4, and we put that in our calculator, and we get approximately 1.28. So when we go to graph it, we've got 3 points. At -1, we have a y of 0.78. At 0, we have a y of 1. And at 1, we have a y of 1.28. Now, from there, you can graph additional points if you want to, but we know what the graph of the exponential looks like. We know it's going to come through this point to the right, and it's going to curve up. And it's going to come through this point to the left, down towards the axis without ever touching or crossing, because we know we have a horizontal asymptote at y equals 0 at the x-axis. All right, here's a few applications. The first one says, the amount of plutonium remaining from 1 kilogram after x years is given by the function w of x is equal to 2 raised to the -x over 24,360. Part A says, how much will be left after 1,000 years? Well, notice x is your years, and y is, or w of x is the amount of plutonium remaining. So we're going to plug in 1,000 for x, and we're looking for the w. So plugging in 1,000, we end up with 2 to the -1,000 over 24,360. Again, we just need to put this in our calculator. You should have a y to the x key or a caret key. And so you can put in your 2 and then your y to the x key or your caret key, and then you'll want to do open parentheses, -1,000 divided by 24,360, and you should get about 0.97 kilograms. So we started with 1 kilogram. 1,000 years later, we still have 0.97 kilograms remaining. So how much will be left after 10,000 years? Same thing, plug in 10,000. So 2 raised to the negative 10,000 over 24,360. Plug that in your calculator. You get about 0.75 kilograms. And on part C, we want to estimate how long will it take for the 1 kilogram to decay to half its original weight. Now, if we were to actually solve that, we want 1 kilogram to decay to half its original weight. Well, if it started at 1, that means we want half a kilogram remaining. And so this time we're looking for how long. We're looking for the X, and we want the W, the amount remaining, to be a half a kilogram. And so 1/2 is equal to 2 raised to the negative X over 24,360. At this point, we would need to solve for X. The problem is we don't know how to solve exponential equations yet. We will learn how in the later sections, but for right now, we don't know how to solve this. That's why the directions say estimate. And so when we're trying to estimate and we don't know how to solve it yet, our easiest option is to guess and check. Now notice after 10,000 years, we were at 0.75 kilograms. So 20,000 years might be a good place to start. So plug in 20,000 for X. When you do, you'll notice it's not quite a half kilogram yet. You're still above it. So that's not going to be enough. So keep plugging in larger and larger and larger numbers until you get to where you need to be. Turns out that if you keep trying, you should find somewhere around 24,000 to 25,000 years is when we're going to end up close to half a kilogram. Again, we'll learn how to solve specifically for the answer later, but for right now, we're just estimating how long it would take. All right, here's another example. Biologists have found that the oxygen consumption of yearly salmon is given by g of x is equal to 100 times e to the 0.7x, where x is the speed in feet per second. Find each of the following. Part A, the oxygen consumption when the fish are still, and part B, when the fish are swimming at 2 feet per second. So pause the video and try this one on your own. Okay, welcome back. On the first one, we're looking for the oxygen consumption when the fish are still. Remember, in our equation, the g of x is the oxygen consumption. X is the speed in feet per second. It's how fast the fish are moving. Well, if the fish are still, they're not moving. And so their speed would be 0 feet per second. So we're looking for how much oxygen are they consuming at 0 feet per second on this first one. So we're going to plug in 0 for x, and we're going to solve for the g. So 100 times e raised to the 0.7 times 0. Again, you should have an e button on your calculator, but notice this is just 0. Anything to the 0 power is 1, and 100 times 1 gives us 100. Now, I'm not sure what the units are here. I'm not sure what unit you use to measure oxygen consumption, and they didn't tell us, so we're just going to leave it at 100. Part B, the oxygen consumption when the fish are swimming at a speed of 2 feet per second. Same thing, we're going to plug in 2 for x, and we're going to solve for g. So 100 times e raised to the 0.7 times 2. If you're going to put this in your calculator all in one step, you're going to want to put parentheses around that 0.7 times 2 so that you end up multiplying that together before you raise the e to that power. And when you put this in your calculators, you should end up with 405.5. And again, I'm not sure of the units, so we'll just leave it without. All right, that finishes the section 5.1 notes.